Another simple problem which we discuss now is problem 4. They want us to prove that if m is bigger than 2, then the value of Euler's phi function, phi of m, is even. I might want to recall what happens if this condition is not satisfied. No, first of all, phi of m, whatever m is anyway an integer because it is defined as the size of reduced residue system. So it's anyway a size of finite set. This is an integer. Just for the record, we know that phi of 1 is 1. This was a part of definition. And what is phi of 2? Reduced residue system modulo 2 consists of one element. This is the number of integers which are smaller than 2 and relatively prime than 2, positive integers which are smaller than 2 and relatively prime to 2. There is only one positive integer, 1, and 1 is definitely relatively prime to 2. So the size of this reduced residue system is 1. It consists of one element. So after that, since this point on, since the next point on, what is phi of 3? A number of positive integers which are smaller than 3, there are only 2 integers smaller than 3, and relatively prime to 3, 1 and 2. 2 of them both turn out to be relatively prime to 3. So there are 2 of them. This is already even, and we want to prove that from this point on, the number phi of m is always even. Here is the proof. We'll consider 2 cases. The integer m may satisfy one of the 2 following conditions. Either there exists an there is an odd prime p which divides m, or m is a power of 2 with some positive integer t. Positive m. At least 3, because when t is 1, m is 2, we say m is bigger than 2. T is at least 2. When t is 1, m is 2. When t is 2 and bigger, m is indeed bigger than 2. Well, indeed, why this is true, why this statement is true? Simply because if the number m is not simply because by the fundamental theorem of arithmetic, the integer m has a decomposition into a product of primes, a unique one, as you remember, and this may be this decomposition, or the decomposition must contain other primes, the primes other than 2. All primes other than 2 are odd. 2 is the only even prime. So we will consider 2 cases. The first Firstly, we'll consider, A, let P divide M, P is an odd prime, then we can write M as P to the S, some power of P times N, with greatest common divisor of P to the S, and N is 1. Well, indeed, this is just the power of P in the decomposition of M into a product of primes. N is not divisible by P, so it is relatively prime with P to the S. P to the S is divisible only by the prime P, no other prime. N cannot be divisible by P, so it has been chosen this way. In this case, we calculate phi of M. We use the fact that phi is multiplicative. So this is the product, because these two are relatively prime. Phi of M is the product of phi of P to the S and phi of N. Phi of P to the S we can calculate as P to the S minus 1 times P to the P minus 1 times phi of N, which is some integer. So S, P divides N, P divides M. So S is at least 1. Otherwise, P does not divide M. So this is an integer. The worst case scenario, S is 1, then this P to the 0 is simply 1. And since P is odd, P minus 1 is even. So since P is odd, P minus 1 is even. Thus, 2 divides P minus 1. 2 divides this factor. Therefore, 2 divides the whole product. This is an integer and this is an integer, so thus 2 divides phi of M means in the case when, what we showed, in the case when there is an odd prime which divides M, phi of M is even. Another case we still have to consider, because it may happen that no odd prime divides M. Then M is a power of 2. And the power is at least 2 because M is bigger than 2. Let us calculate phi of M in this case. This is we know how to calculate phi over power of prime. We did that, we have it somewhere. This is here. I will use this presentation. Now p is 2. 2 to the t minus 1, 2 minus 1, which is simply 2 to the t minus 1. And this number, as soon as t is at least 2, t minus 1 is at least 1, so this is a power of 2, which is of course even. Is even because t minus 1 bigger or equal than 1. T is bigger or equal than 2, so t minus 1 is at least 1. Thus, in either case, this one or this one, we showed that phi of m is even here and is even here.